Welcome to the first flip lecture for CPEN 211 at UBC. In this lecture, we will discuss logic optimization, building upon your knowledge of logic gates from slide Z2. This figure shows several important technology trends related to digital systems design. The top red line in the figure shows the growth in the number of transistors integrated into a single chip on the y-axis versus the year on the x-axis. As you can see, back in the 1970s, a single chip could contain on the order of 1,000 transistors. Today, in 2015, many chips integrate several billion transistors. This exponential growth in the number of transistors per chip is known as Moore's law. Note that this growth in the number of transistors we can implement on a single chip far outpaces the number of engineers per design team. What are the implications of that? Well, one is if that engineers had to directly apply Boolean optimization using the techniques in slide set 1 and 2, it would take far too long to design such a chip, even with thousands of engineers. Instead, engineers specify design using a language such as Verilog, which is then input to a software tool that automatically generates the low-level design. However, to become an effective designer using Verilog, it is necessary to have some understanding of how these tools work internally. This is the motivation for learning the material in this lecture. Another observation is that while transistors are now very cheap, there is a limit to how many transistors we can build on a chip. Hence, we would like to use as few transistors as possible for a given application. In this slide set, we will look at how to reduce the number of gates used in a circuit without changing its behavior. As just noted, generally we let the CAD tools such as Quartus that you use in the labs do this for us. By understanding how a tool like Quartus works internally, you will have a better idea of what matters and what does not matter when writing your Verilog. Before discussing this process of optimizing the implementation of logic functions, we will start by considering several ways of representing combinational logic functions. The learning objectives for this lecture are that by the end of this slide set, you should be able to do the following. Translate a word description of a logic function into a truth table. Define terminology related to logic optimization. Explain algebraic simplification using cube representation of a logic function. Reduce gates for sum of products or product of sums normal form using a Carnot map for both completely and incompletely specified functions. And finally, eliminate hazards in combinational logic. Let's start by considering an example of how we might specify design in English. We will return to the design in this example several times throughout this lecture. In this example, we are interested in prime numbers, that is, numbers that are only divisible by themselves and the number 1. Examples are 2, 3, 5, and 7. We can specify this design using the following English statement. F with inputs DCBA is true if the input DCBA taken together as a 4-bit number is prime. We can specify the same design in other ways. For example, we could also specify this design using a truth table as follows. Here, each row specifies the output of the circuit for a particular combination of inputs. The input bits are listed in order in the first set of columns, and the output is in the right-hand column. For example, the number 3 as a 4-bit number is 0011, which is in the row here. Since 3 is a prime number, the output is 1 in this row. The number 4 in binary is 0100, which is listed in the next row. As 4 is not a prime number, the output listed for it is 0. What is the output Q when the input is 1100?